So in exercise 2041, we're going to do some multi-step syntheses with aldehydes and ketones. So for A, if you look at the reactants and the products, you'll notice one difference, and it's this double bond here. You'll notice that the new bond that you have to form is a carbon-to-carbon bond. So you have to form a bond between this carbon that already existed on the original molecule and this new carbon in this branch. So when you're trying to make a carbon-to-carbon bond, it's kind of nice because there are a limited number of ways to do that, so it narrows down your options. Well, how can you make a carbon-to-carbon bond? You could use a Grignard reagent. That's where you use some carbon chain and you have that bonded to magnesium bromide, and it turns this into a nucleophile. That makes carbon-to-carbon sigma bonds. So if you want a single bond to a carbon, you'd use a Grignard reagent. We don't want that here. We have a double bond to this carbon, so that may not be the best choice. Another way we learn to make carbon-to-carbon bonds is the Diels-Alder reaction. The Diels-Alder reaction takes a diene in the S-cis conformation and the dienophile, and it turns it into a ring. We didn't create a ring in this reaction. We start with one ring and we end with one ring, so we didn't create a ring, so that's probably not going to be our best choice here either. We could do a Friedel-Crafts reaction. That's another carbon-to-carbon bond reaction that we've learned. And you could do alkylation or acylation. In both of those cases, you need some sort of a benzene. And if you treat a benzene ring with just some carbon chain that has a chlorine on it, and then you use AlCl3, that will put the carbon chain onto the benzene. So that's alkylation. And you could also do a similar thing, which is acylation. That's if you have the benzene, and instead of treating it just with a carbon chain, you treat it with an acyl chain. That's where you have this carbon-oxygen double bond group as part of the carbon chain. And that puts, you still need to use the AlCl3, and that ends up putting that acyl group onto your benzene ring. Well, those aren't going to be our choices here because we don't have a benzene ring. So Friedel-Crafts acylation, alkylation, maybe not our best choices. And then this chapter we learned how to make a Wittig reagent. So with a Wittig reagent, you would have to start with some type of an aldehyde or ketone, just some sort of carbonyl, and then whatever carbon chain you want, for example, it could just be one carbon with two hydrogens, you would have to have that double bonded to a triphenylphosphine. So that's 3 benzene rings, which when they're represented as branches are this capital P, lowercase h. So 3 benzene rings attached to a phosphorus, and the phosphorus is double bonded to the carbon. Notice this phosphorus has more than 8 valence electrons. That's because it has d orbitals in it. So the reason for the 8 valence electrons is 2 electrons fit in the s orbital, and 6 fit in the p orbitals, so that adds up to 8. But if an element has d orbitals, like phosphorus or sulfur, then it can have more than 8 valence electrons. So just a note there. What you end up getting is a double bond. It stays on the carbon chain, but instead of going to the oxygen, the double bond now ends up going to the carbon in the Wittig reagent. And so you create a new carbon-to-carbon double bond. Okay, so you know to do Grignard if you're trying to create a carbon-to-carbon sigma bond. So if just one bond between carbons. The Diels-Alder if you're trying to make a ring. The Friedel-Crafts if you're trying to attach some carbon chain to benzene. And the Wittig reagent if you want to make a carbon-to-carbon double bond. Well, that's what we have here. That's what we want to make here. And so whatever else we need to do, we know that we have to use a Wittig reagent to make a carbon-to-carbon double bond. Okay, well, let's make some room. So we know that we're going to do this Wittig. So let's think about what we would need. So notice here, in this case, we're doing that retrosynthesis that we talked a little bit about in a previous video. We're looking at our product and we're thinking, okay, we may not be able to start at the starting material, but what could I start with to create that? Maybe I can connect a previous step to the starting material. So we're sort of working backwards. Okay, what Wittig reagent would I need in order to have that? If you're ever trying to figure out what type of Wittig reagent you need, draw a line through the double bond and draw each of the pieces on either side of that double bond separately. Now you're going to keep the double bond there, but you're going to draw those pieces separately. So that's one, and then that's the other. Right? If I have that orange line there, I've separated those two pieces. So duplicate that. You can draw that twice. And you have two possibilities. In a Wittig reaction, you need an aldehyde or a ketone. That could be on one of the pieces, in this case the ring, or it could be on the other one, in this case the little straight chain. And in addition to the oxygen, you need the triphenylphosphine. So that's this triphenylphosphine there. So that's on whatever double bond the oxygen is not on. So you could have that phosphorus with the 3 benzene rings. And in this one, if the oxygen is on the little chain, then the phosphorus with the 3 benzene rings will be on the ring. So these are our two possible Wittig reagents, but they're not both equally correct. One of these works much better, much better than the other one. Recall in our discussion of the Wittig reagent that to form the Wittig reagent, to form this triphenylphosphine, the phosphorus comes in as a nucleophile and performs an SN2 reaction on a carbon with a leaving group. And that's how you form that Wittig reagent. And so it has all the limitations, forming this has all the limitations of an SN2 reaction. In other words, it works best when the carbon that the phosphorus attacks is not crowded. SN2 reactions require the nucleophile to attack the carbon. If the carbon is really crowded, if it's bonded to a lot of other carbons around it, well, then the nucleophile will have a hard time attacking it and you won't be able to do the SN2 reaction. So if we look at what that's bonded to, if we look at this carbon right here, that's bonded to 2 hydrogens. So 0 carbons are bonded to this carbon right here. On the other side, if we look at what the phosphorus is bonded to, it's bonded to 2 carbons. And because the one on the left has fewer branches, in other words, it's less substituted, this is bonded to fewer carbons, it's less crowded. 0 carbons is less crowded than 2 carbons. And so it'll be easier to form this Wittig reagent on the left. And so that is by far the better Wittig reagent. Okay. So this is what we need in order to, if we have this, then we can make our product. If we have this, these would come together and give us our product. Okay, well, we can make this Wittig reagent without too much trouble. We just need to buy triphenylphosphine. It's like an opaque solid. And then we'll react it with like methyl iodide, and then follow it with butyl lithium. I think we went through the mechanism for that in the previous video. So we don't have to draw all that out now. What we need to follow is the story of this carbon chain here. We'll say, okay, we'll add that as a reagent later, but we need to know how we can make this. Well, when we look at that and we compare it with our original molecule, you'll notice that we've added an oxygen. But it may not be immediately clear how to add an oxygen at this position. Maybe if we had a double bond or something like that. But then you have to start thinking 2 or 3 steps back, and it gets a little hazy. So if you ever get stuck going backwards, then try to think going forwards. Let's say we're stuck here. We don't know what else we can do with that. We know that if we know that we're going to have to do this toward the end of the synthesis, but we don't know how to make this. Okay, well then go back to your reagent, your starting material. It's an alkane. There are only two things that you can do with alkanes. You can light them on fire, in which case they turn into carbon dioxide. That's what happens to your gasoline when you burn it, or what happens to wood or a candle. You light it on fire, you create carbon dioxide. But we don't want to do that, obviously. We want this to stay together. So the only other reaction we can do is we can take this molecule that's really, really stable. There are no extra electrons there. If you search for a nucleophile or an electrophile there, you will be searching in vain. So you take that very stable molecule, unreactive molecule, and you treat it with something that is really reactive. The only thing that will react with an alkane is a radical. Now, a radical is an atom that has an unpaired electron, and we've seen one reagent for radicals several times. We've seen N-bromosuccinimide, NBS, and in this case we'd be using it with some ultraviolet light, so H-nu. H-nu is just a shorthand for light. Remember, there's an equation from General Chemistry 1 that the energy of light is related to a constant, Planck's constant, H, times the frequency of light, which is nu. So the higher the frequency, the more energy light has. So H-nu is just standing in as symbols for light. And NBS, just so it's not a black box, NBS, the N is standing for a nitrogen. The nitrogen has a bromine on it, that's where the B is coming from. And then the S is standing for this other molecule called succinimide. It's a 5-membered ring that has carbonyls right next to the nitrogen. So that's N-bromosuccinimide. And what ends up happening is when you shine the light on this thing, this bond is very weak. It can break very easily because bromine is a great leaving group, and whatever charge is left behind is going to be allylic to two pi bonds, so it'll be really stabilized. So it's easy to shine light on this and have the two electrons here break apart, and you form two radicals. So the nitrogen has an unpaired electron, so it's a radical, and the bromine would have an unpaired electron, so it would be a radical. Okay, this N-bromosuccinimide goes on to live its own life. It's actually not that reactive because the radical is stabilized through resonance over both of the carbonyls. But when this bromine radical runs into your alkane, it attacks it. Now it's going to steal electrons from one of the hydrogens. Those are the things that are most available here. And when it does that, it will leave behind one of the electrons of the hydrogen. And so you'll have a radical on the ring. So let me show you what that would look like. Let's say you have this hydrogen here. The bromine will use its one electron and try to form a bond to that hydrogen. It'll steal an electron from the hydrogen. The other electron in this bond will go onto the carbon. Now remember, I'm drawing this mechanism so that you can understand what's happening, so it becomes a little easier to remember it. When you do this, when you try to come up with the synthesis, you do not have to draw these mechanisms. Drawing a mechanism and devising a synthesis are two separate skills. They overlap like in a Venn diagram, but if you are timed on a test, then you definitely don't have to draw out every step in a synthesis problem. You do in a mechanism. So one of those electrons from that orange bond to the hydrogen now go onto that carbon, and we have a bond to the hydrogen and the bromine. So these two are bonded as hydrogen bromide, and we have a new radical. Okay, well, we'll get rid of that hydrogen bromide. So now you can see where the bromine would attack. So at first, it might have just seemed random that I drew the hydrogen here that the bromine would attack. The bromine could attack anywhere. But when the bromine attacks, it leaves behind a radical. And radicals have the same pattern of stability as carbocations. So tertiary radicals are more stable than secondary radicals, which are more stable than primary radicals. And this radical right here, this radical that we have here, the carbon that it's on, is bonded to 1, 2, 3 other carbons, so it's tertiary. It's the only tertiary position in the molecule. And so that's where that radical forms. Another radical of bromine is formed when light hits another molecule of N-bromosuccinimide, and this second bromine radical can come in, donate its electron to the one that's already there, and give you this. So, long story short, when you treat an alkane with N-bromosuccinimide and light, you add a bromine to the most substituted carbon. So, in this case, we have a primary carbon, tertiary, secondary, 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 secondary. You add a bromine to the most substituted carbon. That's the effect of NBS and light. Okay, well, that doesn't look like this, but it's the only thing that you can do to this starting material. So there's some peace in that, knowing that we did the only thing that we could do. Okay, well, if you compare what we have now to what we want, you'll notice that there's a bromine here that in what we have, and it's not in the ketone that we want to use in our Wittig reaction. In other words, we have to get rid of this bromine. Or to say it in chemistry jargon, we have to eliminate this bromine. So we're going to do an elimination reaction. Now, in an elimination reaction, you have a leaving group, and that's what the bromine is. It's very big, so it can take electrons with it, pop off the molecule, and stabilize the negative charge of those electrons by diluting them over its enormous space. So you have a leaving group. And the other ingredient that you need for an elimination reaction is a base. Now we'll talk about what a base might look like. Okay, bases accept H pluses. They steal hydrogens. So they don't steal in this reaction. The most vulnerable hydrogen is what's called the beta hydrogen. The carbon that has the leaving group on it is the alpha carbon, and every carbon after that is the beta carbon. So we're just using, it's sort of like with numbers, you're using the Greek alphabet. The first letter is alpha, the second letter is beta, hence the word alphabet. We're using those instead of numbers to describe these carbons. So these beta carbons have hydrogens on them, and those are called beta hydrogens. Now notice there's symmetry in this molecule, so the hydrogen on the left and the right are really the same. If you flip this over like a pancake, like you'd flip over a pancake, these switch places, and otherwise the molecule's the same. So I'm just going to consider one of these, since they're really duplicates. Okay, so we have two different beta hydrogens. And the base can attack this, and the base can attack either one of them. So this is a review from Organic 1. The base can attack, for example, the hydrogen on the top. This carbon that has the leaving group on it is slightly positive because the bromine is electronegative. And so the electrons of the hydrogen, when the base tugs on this hydrogen, the electrons are attracted to the slightly positive charge and they kick the leaving group off. So you've eliminated that leaving group. And in that case, you end up getting a double bond going up. So the electrons from that hydrogen create a pi bond in the direction of where the hydrogen was taken. Compare that with this here. The base could have also stolen the other beta hydrogen. Again, the carbon that has the leaving group on it is slightly positive because the leaving group is pretty electronegative. So if the base tugs on this hydrogen, then these electrons are pulled toward the slightly positive carbon and they kick the leaving group off. And what you'd get in this case is a pi bond in the direction of the other beta hydrogen. So we have two possible places where we can form this double bond. Now the truth is, when you do an elimination reaction, you actually end up getting both of those products. So it's kind of messy. But you want one of them to be the major product and the other one to be a minor product. You want one of them is going to be useful to you. That's the one that you want to be a major product. So when you're doing these syntheses, you want to focus on what will give you the major product that you want. Okay, so you can't just do either of these. You want to focus on the one that's going to give you the major product that you want. Well, how do you know? Why would a base prefer one of these hydrogens over another? And that has to do with crowding. So let me erase these details, and let's look at the crowding around these hydrogens. This carbon is only bonded to one other carbon. It is not that crowded. So it's primary. This carbon is bonded to two other carbons. So it is secondary. In other words, this is a more crowded place to be. Okay, so now you can understand how different bases would prefer different hydrogens. If the base is bulky, then it will prefer the less crowded hydrogen because it'll have a harder time getting to the more crowded place. And the bulky base you would want to know is potassium tert butoxide, so TBU-OK. And the tert butyl group, remember, is like this. You have the oxygen, full negative charge, potassium, the full positive charge. On the other hand, if you want to attack the hydrogen that's more crowded, then you need a skinny base. And skinny bases that you learned would be like sodium hydroxide, sodium methoxide, or sodium ethoxide. So this is really the effective base here is either OH minus or replace the H with a small carbon chain. For example, an O in a methyl group in the case of sodium methoxide, or an O with an ethyl group in the case of sodium ethoxide. Those are skinny bases. They can reach this hydrogen here and give you the product that you get here. One other note, one thing that you should be familiar with that's really important in this discussion of elimination reactions is the stability of these products. The more carbons that the carbons in the double bond are bonded to, the more stable the double bond is. Because the p orbitals in the pi bond can overlap with one of the sp3 orbitals on the neighboring carbons a little bit through hyperconjugation, and the electrons can leak out in that direction. When you spread out charge, it stabilizes the molecule. So if you look at this top one, that alkene is bonded to two other carbons, so it's described as di-substituted. If you look at the bottom one, the two bonds in this alkene are bonded to 1, 2, 3 other carbons, so it's tri-substituted. And the more substituted alkene is called the Zaitsev product, and it's the more stable molecule. It's because it's more stable that if you use a skinny base, which could actually attack either of these equally well, that you'll get more of this one than of the other one, because this one is more stable, so it'll stick around longer. The less substituted product is called the Hoffman product, and it's less stable. And you'll only form that Hoffman product if you use a bulky base like potassium tert butoxide. Okay, well, there's a discussion of elimination, a review of Organic Chemistry 1. And if you want more review on that topic, I have a whole bunch of videos for elimination. Just reach out to me and I'd be happy to send those to you. So if you compare what we need to get done, the bridge that we need to the gap that we need to bridge, you'll see that it would be more useful to us to have the double bond going toward where we want the ketone, as opposed to having it go up on this little branch. And so we want this product, the Zaitsev product, and so we're going to use a skinny base. Now, any of these skinny bases would work. I'm going to use sodium methoxide because it tends to show up the most on tests and things. Definitely, though, also know potassium tert butoxide and know the different alkene that it would give you, both in life and for this test. You should know both of those, skinny and bulky bases and the types of double bonds they give you. Well, here we want the Zaitsev product, so we're going to use sodium methoxide. So if we do sodium methoxide, and I'll just sort of make some space. If we use sodium methoxide, it'll steal the beta hydrogen over here, and you'll end up forming that pi bond to that beta hydrogen, the beta hydrogen that the skinny base stole. Let me actually. Okay, so far so good. So next, and once you have that elimination product, you have the double bond going in the right direction, we compare that to the ketone that you need for your Wittig reagent. And you'll see that the difference between these is this one has this oxygen on it, and this one doesn't. And now we're in a position to put the oxygen there because we have some extra molecular glue. We have those pi electrons. We can use those to form a new bond. And specifically, we can do an addition reaction. How do you put an oxygen onto a double bond? You do an addition reaction. Now, we learned two ways in a previous video on synthesizing aldehydes and ketones. We learned two ways to add an H and an OH onto a double bond. The Markovnikov way, where the OH goes on the more substituted double bond, and the anti-Markovnikov way, where the OH goes on the less substituted double bond. We want the oxygen to go on the less substituted double bond. And so we want to do anti-Markovnikov addition. So, anti-Markovnikov addition of H and OH, that's hydroboration oxidation. So the first step is BH3 and THF, and followed by sodium hydroxide and hydrogen peroxide. So if that doesn't sound familiar at all, if that sounds sounds foreign, then definitely go back to that previous video that we had where we discussed the different ways of making aldehydes and ketones. We talked about hydroboration oxidation and how it adds an OH in an anti-Markovnikov way. Okay, so that means that we're going to have our new molecule here. The H will add to the more substituted position, and the OH will add to the less substituted position, that anti-Markovnikov. Addition of H and OH. Now if we compare this molecule with the ketone that we need, the only difference is a bond to oxygen. This has only one bond to the oxygen, this has two, so we need to do an oxidation. Because this is a secondary carbon, because this OH is bonded to a carbon that's bonded to two other carbons, we can use a strong oxidizing agent like sodium dichromate, Na2Cr2O7, with an acid-water wash, so water and sulfuric acid. And we discussed that same reaction in the same video where we discussed hydroboration oxidation on synthesizing aldehydes and ketones. So sodium dichromate with water and sulfuric acid turns a secondary alcohol into a ketone. Once we have the ketone, we can do our Wittig reaction, and we get our product. So overall, the answer for this one is going to be, first, NBS and light. Second, a skinny base like sodium methoxide. Third, so NBS and light will put a bromine on the alkane. Once you have that, you can do an elimination reaction. You can get the Zaitsev product by adding the skinny base. Once we have the double bond, you can do anti-Markovnikov addition of H and OH through hydroboration oxidation, so BH3 and THF, followed by sodium hydroxide and hydrogen peroxide. That gives you this alcohol. To oxidize that to the ketone we would need in our Wittig reaction, we would just add sodium dichromate in a water acid wash. Once we have that ketone, we just have to add it with add the Wittig reagent to it. And we have to be careful that we choose that right Wittig reagent that we figured out. And so that would give us our beautiful, exciting product. Notice in this reaction, it seems long, right? It's definitely 6 steps. It's significant. But notice there's only really one reaction that we're using here that you would have not seen or learned in previous chapters. And that's the 6th step, the Wittig reaction. That's the only thing that's new. You learned about NBS and light or heat in Organic Chemistry 1, and we've used it before in our class to put, for example, a bromine on the benzylic position. You spent a whole chapter learning about elimination reactions in Organic Chemistry 1. You spent a whole chapter learning about addition reactions in Organic Chemistry 1. And oxidation and reduction you learned about in the alcohol chapter, which hopefully you would have done in Organic Chemistry 1, but if not, we have used sodium dichromate to oxidize things like the benzylic position before in this class. Okay, well that's A. So to avoid making this video way too long, I'm going to make A stand alone, and then we'll go on to B in the next video.